Well, good morning. Hello, hello, hello. We are going to be going over homework 8.6, vectors. This is our last section in chapter 8, so that's exciting. And it is going to be a little bit of a longer video. There's quite a bit to go over here. And I think that'll be the hardest part of this lesson potentially for you, is that it's just a lot of new information. You probably have not talked or learned about vectors before. The actual math, I think you'll find is pretty simple, and it's right in line with what we've been doing in chapter 6, much easier than the calculations in 8.5 on the law of sines and cosines. And so the real difficulty will just not panicking at the amount of information and just realizing, getting used to all the definitions. We have quite a few definitions to go over today. So let's jump right in. What is a vector? Well, for all of you Despicable Me fans, you know it is something with magnitude. If you can spell it, magnitude and direction. So that means it's basically an arrow where it's the direction, it's telling you the direction that something is happening, but then also magnitude. And so that means that the length of a vector matters. So that this and this are two different vectors because they are headed in the same direction. We've got two parts here, but they're different magnitudes. Or we could have a third one that might look something like this. Okay, and so these are all different vectors based on their length and their direction. Sometimes they're referred to as a directed segment because they're basically a segment. And that's another point. Notice they're segments so that these are endpoints. They don't go on forever, and this does not go on forever. The length is specific. And so they're not like when you draw a ray and it would go on to assume that it goes on to eternity. This is the length, the power, the amount of a certain thing, a certain quantity going in a certain direction. And so this one's going faster, but in the same direction. This one is going slower and going in an opposite direction. And so vectors kind of, they're used in physics, or they're just used in navigation, describing the direction and the speed. When we say magnitude, it's usually measuring the speed of something in which it's heading in that direction. And so and also the way we would name vectors is we might call this little vector A, and the notation is this little half arrow over the top. So here's our vector A, here's our vector B, and here's our vector C. And so that's how we would name our vectors. Okay, and just a couple, ways of comparing vectors is you can have parallel vectors. Oops, spell parallel right. Double L, not double R. Parallel vectors. Okay, and these are simply vectors, as you guessed it, that have the same direction. Okay, and so if you have these vectors up here, I didn't do it perfectly, but they roughly have all the same direction, even the opposite. So you might want to note that, even opposite. So we've got vector C right here. It's going in the opposite direction, but they all have the same slope. And so that's the other way. It's the same slope. Just like we learned that lines that are parallel have equal slopes. Now, I didn't measure these out perfectly, but roughly, if we rise over run for all of these, should be the same. If I were to add, say, let's add vector D. Okay, vector D would be the one non-parallel vector in these examples. So I could write something like this, and just switch colors because why not? Vector A is parallel to vector B is parallel to vector C. If we're talking about parallel vectors, there's something heading in the same direction. It's okay that one's going faster or slower than the other. It's even okay that one's going in an opposite direction. They're still considered parallel. Then you have equal vectors, and you can probably deduce what that means. And that's just the same magnitude and direction. You'll see there's easy questions on the classwork related to this, and so it's worth going over, though it's not very complicated. So that means they have the same length. That means they have the same speed or magnitude, and they all have the same slope. Okay, and so in this case, they're going to have to be going in the same direction. So you could have, we'll just recreate some more. If we have vector A, and then we have vector B, and then say we have vector C, or even vector D, okay, only the first two, well, let's go ahead and name them real quick. Only the first two would be equal vectors. They would all be parallel vectors as I've drawn them, but only A and B, these would not be equal vectors. Only, whoops, I'm getting excited with my colors. It's a beautiful day. Vector A is equal to vector B. And you'll be able to tell that because they'll be going in the exact same direction and they'll be the exact same length. Okay, so again, not tricky at all. Just realizing what we already know about parallel and congruent segments. Okay, so vectors, magnitude and direction, and they can be parallel, they can be equal, or they can be, scattered all over the place. And again, the length matters, okay, as does the direction. So then we have this thing called component form. One of the ways of describing vectors, we'll be using 2 sheets for today's homework. As you can tell, component form, and all that is, you already know this too. Those look like coordinates. They look like coordinates. They're expressed unlike coordinates with, now they have a V bracket, X and Y. Coordinates, you use parentheses, but you could see that these are, it's the same idea. This is the run and Y is the rise, or the x-axis and the y-axis. So for example, if we have another new component, we'll just call this vector M, and its component form is 2, 3. Again, easy peasy. We can graph that vector by creating ourselves a nice little coordinate plane. Here's my x, here's my y. Okay? And I can just simply put those on the coordinate plane. X and y, over 2, up 3. Over 2, up 3. So vector M would look like this. And that's it. I'm very, very simple. Those are like the points, though again, with a vector it's implied there's a line here now, starting at the origin and line going up from there. So that would be vector M. Or just to do another example, let's say we have vector O. Probably shouldn't use O usually because it looks like a 0, but oh well. Don't tell anybody. And maybe this is -4, 1. And so there's vector O. So then we would just go, this is the X, this is the Y. Get that order just like it's been all year long is very important. So back 4, 1, 2, 3, 4, up 1. So now we have vector O. And the two things we'll be going over next is, other than being able to graph these, is we're going to be able to find the length, the magnitude of these, which again, you already know how to do this. And we'll go over that in just a second. And we're also going to learn how to find the direction of these, and we'll explain that using what we've already learned in chapter 8. So we're just applying a lot of what we've learned in previous chapters as well as this chapter to vectors. But again, expressing them is very easy. One other way I'll show you that they'll be expressed, and I think I can squeeze it in here, is sometimes they will give you a vector in terms of coordinates. They might say, so let's do one more. Let's say they'll say, oh, there's a P, point P, and you'll notice it might, and this is where you got to be a little careful. Point P, that's in coordinate form. That's there in parentheses, and then they'll say it forms a vector with point Q, and that's at 4, 3. Okay, and notice these are not vectors. If they were vectors, this would be one vector and this would be another vector, but these are points, and the 2 points together form a vector. And so let's just find those points. I'm going to go over 7, 1, 2, 3, 4, 5, 6, 7, down 5, 1, 2, 3, 4. All right, well, just ran out of room, but we'll squeeze it in there. And so that's P on the vector. And then Q is at 4, 3, 1, 1, 2, 3, 4, 1, 2, 3. And so that's point Q. And so those two together, I'm just going to turn my paper to draw straighter. This is now a vector. Now what direction is it going in? Well, if they gave me P to Q, then I'm going to do that, P to Q. And so this vector is going in that direction. So they can sometimes ask you to do, you can take 2 points, 2 coordinates, and combine them to make a vector. And the last thing to point out here is, okay, so what would be this vector's, this is vector PQ, what would it be its coordinate or component form? Well, you want to see what is the horizontal change, what is the vertical change, because component form is simply the horizontal change, x, comma, the vertical change, y. So that's pretty easy. I can just count. Horizontally, we went back 1, 2, 3. We went back 3. So it would be -3. And vertically, we went, let's count. We're back 3. We went up 1, 2, 3, 4, 5, 6, 7, 8. We went up 8. So the component form of PQ, which I could write like this, is -3, 8. So usually it can be very basic. You're just graphing them based on the points coming from the origin. But if they give you 2 coordinates, just place those 2 coordinates on the plane and find out the run and the rise. The x change, horizontal change, and the y change, vertical change. And that would be its its component form. Okay? So that is how we express vectors. I'll set that aside and go ahead and move on to the next definition, which is magnitude. So this is still homework 8.6. Now we're talking about what does it mean by magnitude. And again, you already know this, and you might be predicting how we can do that. And again, the magnitude of a vector is its length. The length. Usually that implies it measures the speed. Doesn't always have to be the speed of something. It's the power, it's the energy, it's the strength with which it's doing it. Usually it's something moving in a certain direction at a certain speed. So I'm just going to recreate what I had on the other sheet of paper real quick. We had two vectors. We had vector M that was at 1, 2, 1, 2, 3. I'll go ahead and get red out. So we had vector M. We also had vector O that was at -4, 1, 2, 3, 4, up 1. So this was vector O, because I'm going to use these as examples, continuing with what magnitude. So magnitude would be, so how long are these? How powerful, or what speed would be whatever these objects, bullets, planes, they use kayaks in rivers all the time, boats, somebody running a play, running in straight lines. What is the length of this line? And if you've already seen, we've already done this before, because all that is, here's our right triangles. This is just a hypotenuse. So the magnitude is just the length of the hypotenuse. We know how to find that. So every vector could be drawn, you can do it again here, as the hypotenuse of a right triangle. And in putting it in component form, M was, again, 2, 3. O was, -4, 1. We have the lengths to find that very easily. Because if you remember, the way that you find the length of a hypotenuse is the Pythagorean theorem. A squared plus B squared equals C squared. Okay? So, there it is. So to find the magnitude of M, I can just do 2 squared plus 3 squared equals C squared. Okay, that's going to be 4 plus 9 equals C squared. 13 equals C squared. Plug that into your calculator, find the square root of 13, and you're going to get approximately, C is approximately 3.6. So if this was in miles an hour, this could be something going 3.6 miles an hour. It could be something speeding if it's like in space, 3.6 meters per second or miles per second or whatever. But this is the magnitude of that vector. Again, usually it's speed. And all it is the hypotenuse, a squared plus b squared. And so when you have the component form, you can see it's very quick to find the magnitude. You just square them, add them together, and square root them at the end. Again, we found this by square rooting both sides. Let's go ahead and do, so this is for m. Let's go ahead and find O. Just take the two numbers, -4 plus 1 squared equals c squared. Okay, so that's just 16 plus 1 equals c squared. 17 equals c squared. Square root both sides. So therefore c is approximately, this one I haven't calculated already, so here we go, just to remind us. Use our calculators, square root of 17, 4.1. So this one, as you can see, has a greater magnitude. So if you had to answer the question, which is going faster, first of all, if you don't have to give the amount, you can see this one's a little longer than that one. So this one is going faster. But you can measure it. It is 4.1, whatever the units happen to be. And this is for the magnitude for vector O. So again, you're just using Pythagoras. I just did the same thing twice to find the magnitude. The one other thing you then need to be able to do with vectors is find their direction. And this is where we'll use our SOHCAHTOA. Because the direction is simply the angle made by the vector with the horizontal or vertical axis. Sorry, I'm left-handed, so I always cover what I'm writing. But it's exciting, it's revealed. Horizontal or, it says of, or vertical. And we'll just use the same two examples to build this out. So in other words, I could describe whatever this is, a bird flying, a missile flying, a plane, again, somebody's running, in how fast they're going, the magnitude, or I need to also give its direction. And the direction is simply this angle formed by that vector with the horizontal line. I could also do it here with the vertical line, either one. If by default, I'm going to always go horizontal, but you can do it either way. And you'll see, and it would be a slightly different answer as you see what this means. So all we need to do is find these angles. Well, just to transfer, all we're doing there, I can just sketch it again. You're just trying to find the angle of a right triangle with side length 2 and side length 3. And this, I didn't draw this one to scale because I went quickly. But you can see this is what we've been doing all week. I'm going to go ahead and call the angle we don't know. I'm going to just use this symbol theta, but you could put x. Angles are usually expressed with this little Pokeball looking thing called theta. So how can I find this angle knowing these two side lengths? And again, I just get these from the component form. 2, 3. Let's see. SOHCAHTOA, SOHCAHTOA. From my reference angle, this is opposite and adjacent. So no hypotenuse. So that's going to be, yes, very good. Good, Amalia. Tangent. So I can just simply find the tangent of this unknown direction, unknown angle, equals opposite over adjacent. Okay? And as we've been practicing, how do I undo this? How do I get theta or x by itself? How do I undo tangent? I just need to inverse tangent. And that will give me my theta by itself. So the angle is equal to the inverse tangent of 3 over 2. So let's switch that out, clear the board. Inverse tangent of 3 divided by 2. 56, we're going to round to the nearest whole degree. So 56 degrees. Now, I was about to box it, but we're not quite. We've got to express that. So that means this angle here is 56 degrees. And in terms of direction, we express it as a compass angle. So again, while you have x and y, you could also think of this as north, south, east, and west. north, south, east, and west. So the way you would express this 56 degrees in terms of actual direction, and this is how navigation actually is done at times, is you would say, well, starting from this you look at the two axes of your angle, and starting from east, this is heading east, I'm going east 56 degrees north. So in other words, from east, I've now turned up 56 degrees to the northern direction, and I'm vectoring out in that direction. And so this would be the direction of that vector. The magnitude of it is 3.6. Its direction is east 56 degrees north. And I know that nomenclature might be a little confusing, but you'll get used to it. And we'll do one more example right here. Okay, so for this little guy, again, we'd have, roughly speaking, a triangle looking like this. And you don't have to redraw it. I'm just doing that to have some work down here. But we know that this is 4. And we know that this is 1. Okay, and so we can do, and this is the angle that we're looking for. And so we can do the exact same thing. I'm just going to do it over here, where we can say tangent of the unknown angle, the direction we're looking for, is the opposite. It's always going to be tangent, as you can see. Opposite over adjacent. So the inverse tangent of 1/4. And so I'm just trying to show all the work as neatly as possible. We're going to inverse tangent this. And so theta is, and it actually is approximate because we're rounding. And so let's go ahead and do this again. Clear inverse tangent of 1 divided by 4 equals 14. And that makes sense. Look how small that is. That's a small degree. So 14 degrees. Approximately 14 degrees. Now let's give the direction. This one, notice, is starting headed in the west direction. So west, 14 degrees. And again, from west, it's rising 14 degrees to the north. So west, 14 degrees north. And that would be our direction for our vector. Okay, and so there's quite a bit to vectors, and like I said, it's a lot of information, but it's not, the calculations are not anything that you haven't seen before. You have to, whether they're parallel or equal, you have how to express them in component form, sometimes using coordinates and getting to component form from those coordinates. Then the two big things we have to find are the magnitude or the length of them using the Pythagorean theorem, and then finding the direction using tangent, using SOHCAHTOA. There's another example of questions from homework 8.6, but I'm going to make that in a part 2 just because this was a longer video. So see you in a few moments.